So hi, everyone. Today we have Ezgi, who'll be talking about promotion and cyclic sieving on families of young Tableau. She's from the KTH Royal Institute of Technology. As always, if you have questions, you can either unmute yourself and ask, or just pop it in chat, and I'll be looking at chat as well. So yeah, take it away.
Okay. Well, thanks for inviting me. So Aram mentioned you guys are interested in symmetric functions. So I assumed you guys know about Young Tableau and maybe not so much about cyclic sieving, but you can interrupt me if I assumed wrong. And let's see how long this presentation will take. It's like freshly compiled, still warm. Okay. So cyclic sieving is actually like when I heard the word sieving, I thought it was a method of sieving, but it's not a method. It's actually a property or a phenomenon. We just observe it. It's there. So the way we define it is, let's say we have a set and we have a cyclic action on this set. Then if we have a polynomial and that polynomial sort of records the orbit behavior of the set, we call this cyclic sieving. And specifically what we do is, if the action is of order n, we take a primitive nth root of unity, and then we plug it into the polynomial, and that gives the fixed points of the action. And if we plug in the powers of that root of unity, then we get the fixed points of the powers of the action. But like, it is easier to see it through an example. So let's think of the cyclic action on two element subsets of the first four numbers. So perfectly nice set. And if we act with the cyclic rotation, then we get these two orbits, one orbit of size 4 and one orbit of size 2. And then we'll consider this polynomial 1 plus q plus 2q squared plus q cubed plus q to the 4. And I think it should be 2 instead of 1. Oh, no, that's correct. So if we plug in I or I cubed, we get 0, which says that our action, if we apply it once or 3 times, we get no fixed points. If we apply it twice, that's plugging in I squared, which is -1. That gives us 2, which is the 2 cycle, our 2 fixed points. And if we plug in 1, we get 6, which means that all 6 are going to be fixed points of the action applied 4 times, which is going to be the identity action. So this polynomial with this action and the set has a cyclic sieving property, or we can call them a CSP triple. Well, a question about cyclic sieving is, and it's an interesting question, when do we care about cyclic sieving? Because like at first it might seem like, oh, that's a very nice, very fancy property. And it's certainly interesting when you have this polynomial and you plug in complex numbers and you get positive integers. But actually, if we are given any cyclic action on any set, you can easily construct such a polynomial. So if we have a D cycle, then we can easily construct a polynomial corresponding to that D cycle, which means we wanted to give D when we plug in 1 and 0 the rise. And then this is additive. So for each cycle, we can construct this polynomial and we sum them up, and then you would get a cyclic sieving triple. And in this example, we do a similar thing, I think. Yes, that's where I have the mistake. The first polynomial is 1 plus q squared plus q cubed. The second should be q squared plus q to the 4, which is equal to this 1 plus q squared modulo q to the 4. So we can say that this is not a particularly interesting example of cyclic sieving. Well, the way we get more interesting things is when we do not actually construct a polynomial, but the polynomial is a natural thing that comes up in the theory. This is 2 elements subsets of the set with 4 elements. So we can count this with 4 choose 2. So if we write the same polynomial as the Q analog of 4 choose 2, which it is in fact equal to, then it becomes interesting because this is a very natural polynomial to look at and a natural action, and it turns out they have this connection. Or maybe we can look at a statistic on these subsets. So one statistic we can look at is the sum of the entries in each set. And turns out that also works. These are actually the same polynomial. So if we look at the sum of each subset and sum them up, and we just multiply by power of Q, we get a cyclic sieving property. So these two are more exciting, and it becomes more exciting if it generalizes. Like if we can do the same thing for N and K. And in this talk, we'll mainly be interested in different families of Tableau as our sets, and our action will be the promotion action. And our polynomials, like we'll have different kinds of polynomials, but in Tableau, some interesting polynomials are the simplest cases. You just get the counting formula and you get a Q analog of that. Or you can look at the Schur polynomial, which is a very special polynomial in the context of Tableau, and you can look at specializations of that. Or you can look at a statistic on Tableau, which in our case will generally be the charge statistic. And then you can calculate a polynomial that way. So since our action will generally be the promotion action, let's talk a bit on that. The promotion was originally defined on linear extensions of posets, which is basically the same way it acts on Young diagrams. So the first step is we take a linear extension of a poset, which means our labeling does respect the order of the poset. Then we delete the smallest entry, and then at each step, the smaller one of the upper neighbors falls down. So 3 falls down, and now 8 falls down. And now our empty space is at the top. There is no more falling down to do. So we will decrease 1. We'll subtract 1 from each entry. And now we are just missing an 8. Voila. Now we get a new linear extension. And we can do the same thing again, delete the 1. We have 7, 5, and 3. The 3 falls down, and the 4 falls down. And we subtract 1, and we get a new poset. This is actually what we call the promotion action. And we can repeat doing this action. Well, this was just a random example, and I kept repeating, and I ran out of space. The promotion generally does not have a very small, nice order, though it depends on the shapes. But for this example, I guess it was larger than 14. This is how it works on posets, but it does work the same way on Tableau. And even in the semi-standard case, we can do the same thing, but just respecting the Tableau rules, which is basically what Jeu-de-Token is. This is also called the Jeu-de-Token promotion on Tableau, but for this talk, I'll just refer to it as promotion. And here's an example. We have 2 ones, we delete those. Then at each step, the smaller of the neighbors moves to the empty box. And if we have 2 neighbors which are the same, just like the 2 2s in the third one, then the top box falls down because we want to preserve the Tableau conditions. So we continue like that. The empty boxes get pushed to the outside. Then we subtract one from each at force here, and then we got a new semi-standard Tableau. This is how promotion works on Tableau, but its order can actually be surprisingly high. This was one of the examples we were looking at, the different kinds of ribbons, and when each was on the size 6, the order was 60, then it jumped to 800 million, then to 82 billion, which is quite large because like it is even a lot larger than the number of Tableau you get, and it doesn't decompose into very nice pieces. You get very large primes like 82, which means if we deal with this shape of 12 boxes, you'll get some 83 or larger cycle involved. So it is not always easy to work with promotion on Tableau. That's why the research so far has been focused on some very specific examples where promotion is nice. So there are two types of known cases so far. One is the rectangular shapes of size AB, and there's Brandon Rhodes' paper from 2010. There he shows that if we are looking at standard filling, then promotion has order A times B, and we get a cyclic sieving property, and our function is going to be the Q analog of the counting function, which is the hook length formula. And then he looks at the semi-standard case. So let's say we are using fillings and we are bounding entries by n, and in that case, promotion has order n. This is quite interesting. It turns out the order of promotion does not depend on the shape we are looking at. It depends on the alphabet we are using. And the polynomial we get in this case is the principal specialization of the Schur function times the power of Q. And then in a 2012 paper, they looked at the same standard case with a fixed weight that had some symmetry. So if you rotated d times, you get the same weight. And in this case, the polynomial was the Koska-Folks polynomial. And the Koska-Folks polynomial is going to come up in this talk as well. So we'll talk more about that. And the second case was more recent, and it was the hook shape. So these are the cases where promotions seem to be working nicely. And in this project with Per Alexanderson and Svante Linusson, the idea was, let's look at other shapes where at least the numbers seem to be working out calculationally, and let's see what we can get. So it was more like an exploration. And the things we looked at were straight hook shapes, and then we were looking at skew cases, but only very basic ones where we had disjoint pieces. So disjoint rows and then disjoint rectangles. And then we started looking at some ribbons, and we had some results with small ribbons like 2 rows and some 3 rows. And for hooks and rows and rectangles, we got Koska-Folks polynomials. And for the ribbons, you can see that I have both T and Q. And that means actually that we have an instance of bicyclic sieving where you have double the fun. So you have 2 cyclic actions and then 2 variables. And in this talk, I'll first talk some about the straight hooks, and then if we have time, I'll talk about how bicyclic sieving works and the ribbon cases. Okay. In stretched hooks, we just take a hook shape, which was one of the few examples so far where we had some cyclic sieving, and then we stretch it horizontally. So we replace every box with a row of K boxes. And we'll use a special notation for that for simplicity. But in this case, happily, the promotion operation behaves very nicely. For example, these are the 6 tableaus that are stretched hooks of shape 4, 2, 2. And then we stretched by 2, so we use 2 of each number, and we get 2, 3 cycles. And it turns out this is how promotion acts in general. So the order of promotion is going to be given by a plus b, which is actually the alphabet we are using -1. In the rectangular case, the order of promotion was given by the size of the alphabet. And in these hook shapes, we have the -1. And it is mainly because the ones here do not have a big role. The first K boxes of the first row is always where ones are going to be. They are not going to be moving. In fact, we can actually just get rid of the whole first row and think of it as promotion happening on the rows above. And they would have the alphabet A plus B. And now let's talk a bit about the polynomial we are going to use. And that's the Kotzka-Folks polynomial. Maybe this might be something you guys are more familiar with. So they are the polynomials that come up when we are extending sure functions, sure polynomials in terms of all little polynomials. And we can calculate them via using the Tableau with the charge statistic. And here we are looking at the semi-standard Young tableau of a fixed shape and a fixed weight, and we are looking at charge. And if instead of charge, we look at co-charge, it's a dual statistic, we call the polynomial we get the modified Kotzka-Folks polynomial. And we can just work with one or the other because the sum of charge and co-charge is a constant. So knowing one is also knowing the other polynomial, whichever gives us the nicer numbers. The harder part is how we calculate the charge or co-charge, because it's not a very straightforward operation. It has quite a few steps. Well, we start with a Tableau, and then we look at the reading word. Now, this is a semi-standard Tableau, so we have repeats of numbers, but charge is defined mainly for permutations. So we divide this into standard subwords. And how we do it is we basically go from right to left, finding a 1, then finding a 2, finding a 3, finding a 4, and when we run out of numbers, we just cycle back to the right hand, and we do that till we get all the numbers we can. So here we got 1 and then 2, 3. We went to the other end of the word, found the 4, found the 5. And now that we got all 5 numbers, that's going to be our first subword. We take those out and then we repeat the process. And here in this example, we got 3 standard subwords, each of size 5, but in general, some of them could be smaller if our weight is not, if we are not using each number the same number of times. And then for each of the standard subwords, we'll calculate the charge separately. And to do that, we take a standard subword, we find its descents. And by descents here, I mean the inverse descent, which is what is generally used in the Tableau context. So this the descents are numbers I, where I plus 1 comes before I in the reading word. So 2 comes before 1, that means 1 is a descent. 3 comes before 2, 2 is a descent. 3 is not a descent, and 4 is after 5, so 4 is a descent. So this is going to have descents 1, 2, and 4, and 3 is going to be the non-descent. So we are, as our alphabet has 5 numbers, we'll sum up 5 minus each non-descent for charge, which gives 2, and we'll sum up 5 minus each descent for co-charge, which is 8. And we do this for each subword. Sum what we get to get the charge and co-charge for the Tableau. Well, this is a bit hard to work with, especially when we are also going to be using promotion and we want a connection between them. And like being a descent is a local concept. Like when you want to look at if I is a descent or not, you just check I plus 1, but we need this whole word for partitioning in general. So if you are trying to find if 1 is a descent, you cannot just look at the 2s. You have to look at the 3s and the 4s and the 5s, which makes a lot of work. But in our case, because our alphabet is n to the k, so each number is used the same number of times, it turns out that there is an easier method, which was a happy discovery. So it turns out in this case, it is enough to look at the pairs I and I plus 1. So instead of partitioning the word, we just look at the whole word and calculate how many descents we'll get of each number. So we just look at 1s and 2s, and we delete the pairs that are going to be descents, and we say, okay, one of the ones is going to be a non-descent. We repeat the same thing for 3s and 2s. We keep deleting pairs that are going to be descents, and we are left with 1 pair. And we do this with 3s and 4s, and then this gives us a sequence of how many pairs of non-descents we'll have at the end. And this is going to be a sequence of length k minus 1. And we can just use this sequence to calculate charge instead of the standard subwords. This doesn't work in general, but in our example, because our content is very nice, it works. So we just take this sequence and then we get 4 times 1, 3 times 1, 2 times 2, 2 times 1, and sum them up and get 13. And this is a lot nicer because it is local, and promotion also has a local characterization. But it turns out in our case, it is even more straightforward because we do not have to look at the whole Tableau to get the sequence. For stretched hooks, you can just look at the first row. So you look at the first row, and the number of 2s is going to be your first entry. The number of 3s, the number of 4s, and the number of 5s. So it just depends on the first row. And it interacts very well with promotion. The promotion just rotates the entry. And it makes sense because in this case, promotion is order 4, and we have a sequence of length 4, and promotion just rotates it. So this was working a bit with charge, and to get the cyclic sieving, we made use of a bijection with plain partitions. So the bijection works as follows. You first look at only the ones, and they give the shape 4, and then ones and twos give the shape 6, 2. Ones, twos, and threes give the shape 8, 3, 1. And you keep going like that, recording the shape you get at each step. And that gives you a GT polytope. And the shape you are going to get at the end, it determines what some of the entries have to be. And the sums here are 4, 8, 12. Like the row sums are determined by how many times you use each number. So basically the part that is important is only the part that I showed in bold, which is the plain partition this corresponds to.
Eska, it's been 25 minutes, just as a warning. I have a question though. How does the Gelfand-Zetlin polytope, like how do you get a polytope out of the triangle?
That's a good question. And I actually never thought of that. Can you believe that? Yes, it does say polytope and it should have a polytope connection, but I never considered that.
It's not a polytope. This one is Gelfand-Zetlin triangle. And the set of Gelfand-Zetlin triangle are the integral point inside of polytope. So this is just one instance of one point in the GT polytope.
Okay, so this is like a vertex in the polytope. Okay.
Yes. Not a vertex, an interior point.
Oh, okay.
The GT polytope counts the number of interior points of a triangle that are given by the row sum and the thing like that. So this is a GT triangle.
Okay.
Oh, yes, that does make sense. Okay. So I should probably fix something.
Yes.
Okay, so we didn't come up with this bijection. This was already there, and there is actually an easier way to get a bijection with plain partitions and Tableau, but this is the one that works well because under this bijection, the promotion operation goes to a toggle operation in plain margins. And we're actually in the realm of what is called dynamical algebraic combinatorics right now because it has so much movement. That's where promotions and toggles and all these nice local operations happen. And happily, there was a recent paper with cyclic sieving on these plain partitions. And the polynomial was given by actually the sum of the entries on the plain partition. And this bijection allowed us to actually borrow their cyclic sieving and use it for our ends. We only needed to just connect the statistics we were using because the promotion is already mapped to the toggle operation. And it turns out there is a very easy connection with the charge in our straight hooks and the sum of the entries on plain partitions. And using that, the cyclic sieving in straight hook just follows. And actually, as a bonus, because now we are met to plain partitions and we can just flip the plain partition and the sum stays the same. That means the charge and co-charge is going to stay the same. And that gives us a way to connect what happens to the straight hooks if we flip A and B. That was the idea on that part. And For the ribbons, as I promised you, I'll talk a bit about the bicyclic sieving. Now, instead of one, we have two cyclic actions of different orders. And then for each cyclic action, we take a primitive root of unity. And then if we can find a polynomial on these two variables, q and t, such that if we plug in two roots of unity, we get the points that are fixed by application of these two actions. And we say that this triple has the bicyclic sieving property. I guess this will also work better with through an example. So one thing you were looking at was ribbon tableau, which was just saying that the shape is a ribbon. It does not contain any 2x2 boxes. And here we are looking at the ribbons where we have 2 boxes on the top row and 4 boxes on the bottom row. And we are just looking at the standard filling, so we use each number exactly once. And in this case, what we get is a 5 cycle, a 6 cycle, and a 3 cycle. But what makes these easier to work with is we generally don't get any interaction between the two rows when we are doing promotion. So mostly, nothing, when we delete the smallest entry, nothing falls down from the top row to the bottom row. It only happens in this one specific case, which is the first tableau here, 2, 3, 1, 4, 5, 6. This is actually the only tableau where I delete the smallest entry, and then the top box falls down. In all the other cases, the smaller one will be the horizontal neighbor. So we'll just basically be doing promotion on the bottom row and the top row separately. And this one tableau, it gives the 5 cycle, and the others are going to give cycles of order divisible by 6. In this case, 1 6 cycle and that divides 6. 1 6 cycle and 1 5 cycle. And when these are behaving independently, you can just think of it as promotion happening on one of the rows, because the other rows is completely determined by what happens on the first row. So this is sort of the same thing as just looking at the 2 element subsets and then doing promotion on those, or rotating entries. So if you look at the 6 cycle, the top row is 1 3 2 6 1 5 4 6 3 5 2 4. This is not exactly rotation, but this is just the cyclic sieving on this 2-box mini rectangle. So yes, this is not exactly the same as the subsets, but it's a similar idea. So it has the same structure minus 1 cycle. So what we have here is we get the cycle structure of this one row. We subtract 1 6 cycle and we add 1 5 cycle instead. And that means we have the original structure of the cyclic sieving, and instead of promotion, we can use promotion to the power of 5, because for cycles of order dividing 6, promotion and promotion to the power of 5 act the same way, at least orbit structure wise. And for the 5 cycle, we can think of this as the action of promotion to the power of 6. And so how this works is basically when we have these actions of promotion, we have 2 types of orbits, and the order of promotion in these 2 parts is relatively prime, then we can write it as a bicyclic sieving phenomenon. And happily this generalizes, so it turns out if we have any 2-row ribbon, then there's going to be this one tableau where when we do promotion, the 2 rows interact. And for the others, it's the 2 rows will have promotion separately. So we have the structure of the promotion on just one of the rows, which is given by the Q binomial of M choose B. And then we subtract 1 cycle. And then instead we add a cycle of size m-1. And then we worked on the 3-row ribbon case, and we only get some similar results where we had relatively simple 3-row ribbons where the first and last row just had 1 box. In this case, again, we mostly get cycles of size m-1, but we get this one special cycle when we have a different interaction. And the orders of promotion are going to be relatively prime, so we can see this also as a bicyclic sieving property. And okay, I think I'm a bit early because there hasn't been a lot of time since the break, but this is basically all the material I prepared. I thought it would take longer. If you found these things interesting, these are some references on general references on dynamical algebraic combinatorics. The first 2 are both really nice. And then this is Bruce Sagan's Cyclic Sieving survey, and that does include a lot of examples. And more specifically, this is our paper with Per and Svante. And Brandon Roll's paper, like this is the main paper where he did the rectangular Tableau case. So I guess that's one of the most important papers in the subject. And this is Stanley's promotion and evacuation, which is evacuation is repeatedly applying promotion. Yeah, thank you.
Awesome. Let's thank the speaker.
You forgot your trick.
But you're the only one who unmuted. Everyone else was muted. So I was like, okay. Why do you unmute so quickly, Nantal?
Because I didn't think.
That's okay. Are there any questions? So while people are forming questions, I guess I do have one. So you said you have this for the 3-row tableau or 3-row ribbon tableau where the top and the bottom row only have 1 cube or block.
Yes.
Is there any hope to kind of do this for kind of arbitrary ribbon tableau, or
well,
like to figure something out?
Yes, we actually did try this case of like 2, 2, 2, 3, 3, 3, or k, k, k in general. And then when we solved the numbers, we were a bit discouraged. The methods that we used in this 3-row case was very basic. So like, how does promotion act? And it's just trying and seeing. And that method doesn't generalize. It is possible to get a general case, but I don't think you can get one via that method, because when you look at larger cases, then the rows start interacting, and you have to take that into account. The cases we did were when that was minimal, so it did like you could think of them as separate rows or separate instances of promotion mostly. So I don't know how to think about it. Like, why would a 67 or 83 cycle come up?
Okay, that makes sense.
Yeah, in some instances, the cycles are suddenly super large for no reason.
Yeah. All right. Are there other questions? All right. Seeing none, let's thank the speaker again.
This
Well,